Okay, so today we're going to continue our study of number theory. And for this lecture, we're going to focus on prime numbers. Okay. Okay, so let's start with a definition of a prime. So a positive integer greater than 1 is called prime whenever the only factors so I'll call this a positive integer n greater than 1 is called prime whenever the only factors of n are 1 and itself. If n is not prime, then n is called a composite. N is composite. Okay, so we have the definition of being prime, and then also the definition of being composite. So every positive integer greater than 1 is either prime or composite, which leads me to a very important theorem. Okay. This actually has a name. This is called the fundamental theorem of arithmetic. Okay. And it states, so every positive integer greater than 1 is either prime or can be written uniquely as a product of two or more prime numbers. Okay. So, for example, maybe consider the composite 999. Okay, this can be written as 3 times 3 times 3 times 3 No, 3 times 3 times 3 times 37. Okay. So, all right. It's, I guess, a nice property about positive integers. If you're either prime, it can be written uniquely as a product of prime numbers. So notice that each of these are prime. And typically, when we write out the prime factorization of a composite, we will list the primes in order, in increasing order. Okay? So that's often added to this theorem statement. Okay, so, all right, well, why are primes special? Well, it's because primes are sort of like the atoms of the integers, right? Every integer is made up of primes in a very unique way, right? So, well, how many primes are there, right? So if we started to list off all the primes, so the first prime would be 2, the second prime is 3, the third prime is 5, and then 7, and then 11, right? And then 13. How many primes are there? Is there any kind of pattern to them, right? So I would like to share my screen with you real fast. So I wrote a simple program in Python to kind of show how many primes there are relative to composites. So let's look up to 10. So over here, so you'll see this plot here. So the blue line represents the number of primes less than or equal to a given number, n, and the orange line represents the number of composites less than or equal to a number n. So here we see there's 1 prime less than or equal to 2, and there's 0 composites less than or equal to 2. And then here's 3, so then there's 2 primes less than or equal to 3, and there's 0 composites less than or equal to 3. And at 4 is not prime, but it is composite, so you see that the line lifts up. So these lines here are just showing us how many primes are less than or equal to n, that's the blue line, and how many composites are less than or equal to n, that's the orange line. Okay, so that's 10. Maybe let's look at up to 20 now. Okay, we see that the number of composites is growing, the number of primes is still growing. Okay. What about if we go up to 50? Okay, we see the number of primes is kind of dying off. What about if we go up to 100? Still, the number of primes is kind of dying off, the number of composites is growing. What if we go up to 1,000? Take a while for that to run, and then we see that the number of composites keeps on growing, but the number of primes is kind of dying off. Right? Like, is it ever going to be over 200? Let's see. Let's go to 2,000. So let's go to 2,000. It'll take a second to run. Okay, so it just ran. And it looks like the number of primes less than 2,000 is barely, it's not even at 250, but the number of composites is like way up here, closer to 2,000, right? If I keep on going, right, like 2,500, I can only go so far because it takes time to check whether or not a number is prime or not. It's difficult to determine if the number is prime. And it looks like the number of primes is dying off, right? The number of composites is just growing, it looks like in a very linear fashion, like maybe 1/2 of x would plot this line or something like this. But here, this is definitely not looking like it's growing fast enough, right? So one immediate question that you might ask if you start looking at these examples is that is there an infinite number of primes? Like, why would there have to be an infinite number of primes? Because it looks like numerically when you run these tests that we keep on going, and this line looks like it might level out eventually. Right? Well, it turns out that there are an infinite number of primes, and I'm going to show you the proof. So remember the fundamental theorem of arithmetic. Every number is either prime or can be written uniquely as a product of prime numbers, or two or more prime numbers. Okay, so here's the theorem. There are infinitely many prime numbers. So this answers the question of whether or not the primes die off as you go off to infinity. Okay, and then also, so if you recall, when we looked at the proof that the square root of 2 is irrational, I said that that was proof number 1 from what's called the book, Paul Erdős's book. And a lot of people argue that if you turn the page to proof number 2 of this fictional book, this proof would be on page 2. So let's go ahead and look at this. And again, this is one of these theorems that all math majors should know. So if you graduate with a math degree and you don't know this proof, then you really didn't learn what you should have learned. So we're going to do this by contradiction. So by way of contradiction, suppose there are a finite number of primes say, I don't know, n of them. Okay, so there's n prime numbers. So a finite number of them, say n of them. Okay. So then we can say, so under this assumption, we may list all primes in increasing order as P1, which would be like 2, P2, which would be the prime number 3, so forth and so on, Pn. Pn is the largest prime. Okay. So we can just, it's a finite number of them, we can put them in this finite list in increasing order. So that'd be 2, 3, and then 5, and then 7, so forth and so on until we get to Pn, which is the largest prime that exists. So we're assuming for contradiction there is a finite number. All right. So next, let Q be equal to the product of all primes plus 1. Okay, so if there's a finite number of primes, then we can surely multiply them all together and add 1, and we get this number Q. Okay. So, by the fundamental theorem of arithmetic, by fundamental theorem of arithmetic, Q is either prime or can be written as the product of 2 or more prime numbers. Right, so the fundamental theorem of arithmetic guarantees that number Q is either prime or can be written as a product of 2 or more prime numbers. But note, since we're multiplying Pn here by positive integers, and we're adding 1, Pn is the largest prime, right? So Q is strictly larger than Pn, so Q is larger than the largest prime, so Q can't be prime. So we can say, since Q is strictly greater than Pn, Q cannot be prime. Hence, Q has at least 2 prime factors. Okay, so it's a composite, in other words. Q is a composite, it's not prime. So we're going to say, let Pj be one such prime factor. And so, since Pj is a prime factor of Q, we know that Pj divides Q. Okay. Okay. However, um, PJ also is a factor of this product of P1 times P2 times dot 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 times Pn. Because this is the product of all prime numbers, and Pj is a prime number, so it's in there somewhere, so it's a factor of it. And so Pj divides this number. Okay, now finally, since Pj divides Q and Pj divides this product, it follows that, I have room to write it over there, it follows that Pj divides Q minus P1 times P2 times times Pn, but that's equal to 1. Right? Q is defined as that product plus 1, right? And okay, so if we subtract that product on both sides, we get that minus that is equal to 1. Okay, so if Pj divides that, if Pj divides that, then surely it divides the difference, because you could just factor out a Pj from there and a Pj from there, and it would divide it. This is a contradiction since no prime number will divide 1. Okay. The primes start at 2. So none of those can divide 1. I mean, by division, we're talking about integer division. Okay? So this is a contradiction since Pj cannot divide 1, but it also divides 1. So it follows that there must be a infinite many number of prime numbers. So I guess I'll just finish it off. So it follows that there are infinitely many prime numbers. Done. Okay. So this is a clever proof by contradiction. Hopefully you understand it. And it verifies that there must be an infinite number of prime numbers. Okay. Okay, so that will be it for today. I guess that's our introduction to prime numbers. I'll try to post another video tomorrow that continues this study. So, but for today, I'd like it for you to watch this lecture and then go to the YouTube folder on Blackboard, and I posted a Paul Erdős documentary. So after you watch this lecture, watch that documentary. As a part of your second exam, I'm going to have you write a short summary of that documentary. Okay? All right, everyone stay safe, and I will see you next week.